Students, let us continue from where we left. We were discussing the problems on examining the continuity of the following functions at the specified point. Before I go to the next problem, let me just explain the mark distribution from this chapter. This is a very important chapter both from PU exams point of view as well as from any of the competitive exams, whether it is CET or mains, advanced. This is a very important chapter. As far as PUC is concerned, you can expect one question from 1 mark, and 2 marks 2 questions, 3 marks 2 questions, 4 mark 1 question, and 5 mark 1 question. So altogether, you can expect 20 marks questions from this chapter. So this chapter is very important, not just from examinations point of view, which you have seen already. Other than that, from the subject's point of view also, this is a very important chapter. Okay, so let us go forward. Let us consider another function where we are asked to check the continuity of that function at a given point. Okay. The next function what I am talking about is say f of x is equal to step x at x equal to 1. We have seen a similar example of it in the last class. F of x equal to step x at x equal to 1. We are asked to test the continuity of this function at x equal to 1. Okay. So now I will find out left hand limit. Left hand limit is equal to limit x tends to 1 minus f of x. That is equal to, as x tends to 1 from left side. When I write x tends to 1 minus, its meaning is that x is approaching 1 from left side. When x approaches 1 from left side, what happens to step x? For that, let us just have a look at the graph of step x. Step x, or the greatest integer function. This is a very well-known function. From 0 to 1, it is 0. From 1 to 2, at 1 it will be 1. From 1 to 2, it is 1 itself. From 2 to 3, it is 2. At 2, it is 2. From 2 to 3, it is 3. In this. This is the graph of step x. Now we are talking about the continuity. We want to discuss the continuity of this function at x equal to 1. So first we are talking about left hand limit. Left hand limit means x is approaching 1 from left side. So when x approaches 1 from left side, x is very close to 1 but less than 1. So when x is very close to 1 but less than 1, then the value of step x will be equal to 0. Because when I say x is very close to 1 but less than 1, its meaning is x may take the value 0.9, 0.95, 0.999, etc. Then right hand limit, that is equal to limit x tends to 1 plus f of x, which is equal to limit x tends to 1 plus step x. That's equal to. Observe here, when I say x is approaching 1 from right side, x tends to 1 plus, it means that x is approaching 1 from right side. So x is very close to 1 but greater than 1. So when x is very close to 1 but greater than 1, x may take the values 1.1, 1.05, 1.01, 1.001, etc. At all those points, value of step x will be equal to 1. As we observe, the left hand limit is equal to 0 and the right hand limit is equal to 1. So left hand limit is not equal to right hand limit. Hence, limit itself does not exist. Then there is no point in checking whether limit is equal to the functional value or not. So limit x tends to 1 f of x does not exist. Therefore, this function is discontinuous at x equal to 1. We can also say 1 is a point of discontinuity, which is very evident from this graph also. As x approaches 1 from left side and from right side, f of x is approaching 2 different values, so limit does not exist and hence the function is discontinuous at x equal to 1. As I have already mentioned in the last class, not only at 1, at all integers this function is discontinuous, and at all non-integral points this function is continuous. Let us look at the next question. F of x is equal to 2x square minus 3x minus 2. F of x is equal to 2x square minus 3x minus 2 divided by x square minus 4 whenever x is not equal to 2, and it is 3 by 2 when x is equal to 2. When x is equal to 2, it is 3 by 2. At x equal to 2. See, here we are asked to examine the continuity of this function at x equal to 2. At x equal to 2, whether this is continuous or not, that we will find out. Okay. So for this problem, we can directly find the limit. Limit x tends to 2 f of x. Here we need not go for finding left hand limit and the right hand limit separately. Limit x tends to 2 f of x. F of x is 2x square minus 3x minus 2 divided by x square minus 4. Okay. So if I directly apply the limit, this will become 2 square 4. 2 into 4 is 8. Minus 3 into 2, we get minus 6 here, minus 2. 8 minus 6 minus 2, which is 0. And denominator 2 square 4 minus 4, which is also 0. 0 by 0 is an indeterminate form. So now what do? We will factorize this. We will factorize that numerator. I will do it here. 2x square minus 3x minus 2. Let us factorize this quadratic factor. When we multiply, we should get minus 4x square. When we add, we should get minus 3x. So I will write 2x square minus 4x plus x minus 2. So 2x into x minus 2 plus 1 into x minus 2. So that will give you 2x plus 1 into x minus 2. Okay, let us substitute here. Limit x tends to 2. This 2x square minus 3x minus 2, I will write that as 2x plus 1 into x minus 2 divided by x square minus 4 we have. I will write 4 as 2 square, and x square minus 2 square can be written as x plus 2 into x minus 2. So now that x minus 2 gets cancelled, hence we have this is equal to limit x tends to 2, 2x plus 1 divided by x plus 2. Apply the limit as x tends to 2, we get 2 into 2, 4 plus 1, which is 5, divided by 2 plus 2, that is 4. So, what we have here is that limit x tends to 2 f of x is equal to 5 by 4. And what is f of 2? At x equal to 2, the function is defined as 3 by 2. Okay? So, limiting value is 5 by 4 and the functional value is 3 by 2. They are not equal. Limit of f of x as x approaches 2 is not equal to f of 2. Therefore, this function is discontinuous at x equal to 2. Okay. Let us discuss the next question. F of x equal to 5x square minus 4x, 4x square minus 3x, 5x square minus 4x whenever x is greater than or equal to 1, and 4x square minus 3x when x is less than 1 at x equal to 1. This is the question. Okay. So f of x is equal to 5x square minus 4x whenever x is greater than or equal to 1, and f of x is defined as 4x square minus 3x whenever x is less than 1. So at x equal to 1, we have to test the continuity of this function at x equal to 1. So first we shall find the limit. For that I find out the left hand limit and the right hand limit separately. Left hand limit, this is equal to limit x tends to 1 minus f of x. Its meaning is that x is approaching 1 from left side. When x approaches 1 from left side, there x is less than 1. So whenever x is less than 1, the function is defined as 4x square minus 3x. That you can take here. Apply limit here. As x approaches 1, 4x square minus 3x. Put x equal to 1, 4 minus 3. Get 1. Left hand limit is 1. Now right hand limit, that is equal to limit x tends to 1 plus f of x. That's equal to limit x tends to 1. X tends to 1 plus f of x. X is approaching 1 from right side. So there x is greater than 1. Whenever x is greater than 1, the function is defined as 5x square minus 4x. Now if I apply the limit, I am going to get 5 minus 4, which is equal to 1. So left hand limit is equal to right hand limit. Hence I can say limit x tends to 1, f of x is equal to 1. Then what is the value of f of 1? At x equal to 1, how it is defined? Say whenever x is greater than or equal to 1, the function is defined as 5x square minus 4x. So at x equal to 1, this is what it is defined. Put x equal to 1 here, we get 5 minus 4, which is equal to 1. So limit x tends to 1, f of x is equal to f of 1. Therefore, f of x is continuous at x is equal to. Okay, let us discuss the next question. F of x is equal to 1 minus cos mx by x square when x is not equal to 0. F of x is equal to 1 minus cos mx by x square when x not equal to 0, and it is m square by 2 when x is equal to 0 at x equal to 0. So here in this question we are asked to check the continuity of this function at x is equal to 0. Okay. So let us find out the limit now. Limit x tends to 0, f of x. Again, no need to find out left hand limit and right hand limit separately here, because whenever x is not equal to 0, function is defined as 1 minus cos mx by x square. Its meaning is that to the left side of 0 as well as to the right side of 0, f of x is defined as 1 minus cos mx by x square. Only at x equal to 0, it is defined as m square by 2. Okay. So limit x tends to 0, f of x, that's equal to limit x tends to 0, f of x. What is f of x? 1 minus cos mx divided by x square. Now if I directly apply the limit here, we are putting x equal to 0, we get cos 0 here. Cos 0 is 1, 1 minus 1, numerator is 0. Denominator, if I put x as 0, denominator is also 0. So this is 0 by 0 and indeterminate form. Okay. So then what else can I do? Directly I cannot find the limit. So let us use some trigonometric formula which we have used, which you have learned in the last year. 1 minus cos mx. So I can think of this formula. 1 minus cos theta. 1 minus cos theta is equal to, yes, anybody? Yes, you are right. 1 minus cos theta can be written as 2 sin square theta. As we know, 1 minus cos theta equal to sin square theta by 2 and 1 plus cos theta is equal to 2 cos square theta. So here this looks like 1 minus cos theta. In place of theta we have mx here. So I will use this formula. 1 minus cos theta is 2 sin square theta by 2. This will give you 2 sin square theta by 2. That is mx by 2 divided by x square. 1 minus cos theta is 2 sin square theta by 2. So 2 sin square mx by 2. Okay. Now this is equal to, I continue here. Limit x tends to 0, 2 sin square mx by 2 divided by x square. We can think of another formula in limits, that is limit theta tends to 0, sin theta by theta is equal to 1. This is a very well known formula to all of you. Limit theta tends to 0, sin theta by theta is equal to 1. This formula we know. Okay. So now here we have sin square mx by 2 in the numerator. So see, from this we can also write like this. Limit theta tends to 0, sin square theta by theta square, that is also equal to 1. Because this can be written as sin theta by theta. As theta tends to 0, sin theta by theta becomes 1. Here sin theta by theta whole square. So here 1 square, which is also equal to 1. So now here you observe we have sin square mx by 2. So what do you prefer in the denominator? When you have sin theta in the numerator, we want theta in the denominator. And when we have sin square theta in the numerator, we want theta square in the denominator in order to use this formula. So coming to this expression here, we have sin square mx by 2 in the numerator. Therefore, we need mx by 2 whole square in the denominator. So, I will multiply and divide by that factor. Limit x tends to 0. 2 I will retain as it is. Sin square mx by 2 we have. We want mx by 2 whole square, that is right, into m square by 4. Okay, see what I have done. This x square, if I simplify this, I am going to get m square x square by 4. Here we have m square by 4. So that m square by 4 gets cancelled. We will be left with x square. So I have not done anything extra. We had x square here. We wanted mx by 2 whole square here. So what did I do? I have multiplied and divided by m square by 4. That m square by 4, I wrote it as m by 2 whole square. So together with this x square, it has become mx by 2 whole square by mx by 2 whole square. I multiplied and divided by m square by 4. Now, as x tends to 0, this factor, it looks like sin square theta by theta square. As x tends to 0, this expression becomes 1. So you have 2 into 1 into m square by 4. 2 gets cancelled. This will give you m square by 2. So therefore, limit x tends to 0, f of x is equal to m square by 2. And what about f of 0? F of 0 is the value of the function at x equal to 0. F of 0 is equal to m square by 2. Okay, so limit x tends to 0, f of x is m square by 2 and f of 0 is also m square by 2. Therefore, we can say, now observe that these two are equal. I will write here, limit x tends to 0, f of x is equal to f of 0. So, f of x is continuous at x is equal to 0. Let us look at the next question. F of x is equal to mod x plus 3 whenever x is less than or equal to minus 3, and it is minus 2x when x is greater than minus 3 but less than 3. 6x plus 2 whenever x is greater than or equal to 3. Now here we are asked to check the continuity at 2 points, at x equal to 3 and also at x equal to minus 3. Okay. So the function is defined like this. It is mod x plus 3 whenever x is less than or equal to minus 3, and it is minus 2x when x is greater than minus 3 but less than 3, and it is 6x plus 2 whenever x is greater than or equal to 3. How? See here, mod x. Mod x, we know the definition of mod x. It is defined as x if x is greater than or equal to 0, and minus x if x is less than 0. Mod x is equal to x wherever x is greater than or equal to 0, and it is minus x when x is less than 0. Okay. So now here we have defined f of x as mod x plus 3 whenever x is less than or equal to minus 3. X is less than or equal to minus 3 means whether x is positive or negative. Yes, you are exactly right. X is negative. So when x is negative, I can replace mod x with minus x. So here I am replacing mod x with minus x. So this f of x can be written as minus x plus 3 when x less than or equal to minus 3, minus 2x when x is greater than minus 3 but less than 3, and 6x plus 2 when x is greater than or equal to 3. Okay. So here they have given 2 points. We want to check the continuity at 2 points. So I will take one by one. So first I will take minus 3 at x equal to minus 3. We want to check the continuity of this function at x equal to minus 3. For that I will go for left hand limit now. Left hand limit extends to minus 3 minus. When I write minus 3 minus, don't think that this minus into minus will become plus and we get plus 3. No, it's not correct. This minus, what I have written here, that minus indicates that x is approaching minus 3 from left side. Okay. So x is approaching minus 3 from left side. When x approaches minus 3 from left side, its meaning is that x is very close to minus 3 but less than minus 3. X is less than minus 3. When x is less than minus 3, the function is defined as minus x plus 3. Apply the limit here, minus x plus 3, minus of minus 3 will give 3 plus 3, that's equal to 6. Left hand limit is 6. The right hand limit I write here, that's equal to limit extends to minus 3 plus. Its meaning is that x is approaching minus 3 from right side. That's equal to limit extends to minus 3. X is approaching minus 3 from right side means x is greater than minus 3. X is very close to minus 3 but greater than minus 3. So when x is greater than minus 3, it is defined as minus 2x. So apply the limit here, minus 2 into minus 3, that will give you 6. Left hand limit is 6, right hand limit is 6. So limit exists. I can write limit extends to minus 3 f of x is equal to 6. Then what about f of minus 3? F of minus 3 means the value of the function at x equal to minus 3. So whenever x is less than or equal to minus 3, it is defined as minus x plus 3. So f of minus 3 at minus 3, this is what we have to consider. Putting x equal to minus 3, we get a minus of minus 3 which is 3 plus 3, that is 6. So limit extends to minus 3, f of x is equal to f of minus 3. So according to the definition of continuity, we can say that the function f of x is continuous at x is equal to minus 3. Okay. So they have given 2 points, 3 and minus 3. First we have tested at x equal to minus 3 and we have seen that at x equal to minus 3 the function is continuous. Okay. Now let us look at the continuity. Let us examine the continuity at x equal to 3. Okay. So at 3 I want to test the continuity. So first left hand limit. X is approaching, limit extends to 3 minus f of x. Its meaning is that x is approaching 3 from left side. When x approaches 3 from left side, x is very close to 3 but less than 3. X is very close to 3 but less than 3. Then in that region, f of x is defined as minus 2x. So this is equal to limit extends to 3. X is approaching 3 from left side. So there it is defined as minus 2x. That I substitute here. Minus 2 into 3. That will be your minus 6. So left hand limit is minus 6. Now I would like to find the right hand limit. Limit extends to 3 plus f of x. That's equal to limit extends to 3 f of x. X is approaching 3 from right side. Means it should be greater than 3. Whenever x is greater than 3 or equal to 3, the function is defined as 6x plus 2. Now if you apply the limit here, 6 into 3, 18 plus 2, that will give you 20. So we observe that limit extends to 3 f of x. Observe here, left hand limit is minus 6, right hand limit is 20. They are not equal. Therefore, limit extends to 3 f of x does not exist. When the limit itself does not exist, then there is no question of it being continuous at that point. When the limit does not exist, when the left hand limit is not equal to right hand limit does not exist. See, for the existence of, for a function to be continuous at a particular point, not only limit exists is enough, along with it, the functional value must also be equal. Left hand limit must be equal to right hand limit, must be equal to the functional value. Then only we can say that the function is continuous at that point. So here we observe that limit does not exist. Therefore, f of x is discontinuous. Discontinuous at x is equal to 3. Okay? At minus 3 it is continuous and at x equal to 3 it is discontinuous. Okay. So now I think students, you have understood how to check the continuity of a given function at a particular point. Let us move forward. Let us look at some of the theorems on continuity. Algebra of continuous functions. Algebra of continuous functions. There is a theorem here. The statement of that theorem, that is, let f and g be two real functions. Real functions. Let c be a real number. Let c be a real number. Then Let f and g be two real functions. Let c be a real number, and let f and g be continuous at c. Okay, so at this particular point at c, f and g are two real functions. C is any real number. In other words, c is any point in the domain of f and g, where the function f and g are continuous at x equal to c. At that point c, the function f as well as g is continuous. Then we can say f plus g is continuous. F plus g is continuous at x equal to c. F minus g is also continuous at x equal to c. F into g is again continuous at x equal to c. F divided by g is also continuous at x equal to c, provided the denominator, provided g of c is not equal to 0. Provided g of c is not equal to 0. Because if g of c is 0, then the denominator becomes 0. This becomes indeterminate form. So this theorem tells us that if f and g are continuous at a particular point, then f plus g is continuous, f minus g is continuous at that point, f into g is continuous, and f by g is also continuous at that point, provided the denominator g of c is not equal to 0. Okay. The proof is very simple, and therefore it is not a part of the syllabus. See, given that f and g are continuous, I can say limit extends to c, f of x is equal to f of c, and limit extends to c, g of x is equal to g of c according to the definition. See, they have defined that f and g are continuous functions at x equal to c. Therefore, limit extends to c, f of x is equal to f of c, and limit extends to c, g of x is equal to g of c. Now, to prove the first one, I will consider limit extends to c, f plus g of x. Okay, limit extends to c, f plus g of x. This is nothing but according to the property of limits, we can write this as limit extends to c, f of x plus limit extends to c, g of x. So here we know that limit extends to c, f of x is f of c, and limit extends to c, g of x is g of c. This is nothing but f plus g of c. F of c plus g of c is nothing but f plus g of c. So we have seen that limit extends to c, f plus g of x is equal to f plus g of c. Therefore, f plus g is continuous at x equal to c. Similarly, we can prove the other results also. But anyway, this is not there in our syllabus, so we need not worry about it. Just concentrate on the statement of this theorem. Let me explain again. So, what this theorem tells us is that if f and g are two continuous functions at a particular point, then f plus g, f minus g, and f into g are continuous at that point. And f by g is also continuous at that point if g of c or g of whatever the point you take is not equal to 0. Okay. So from this we can come to one conclusion, that is, so by using this theorem, we can write a note, that is, if f is continuous at c, then minus f is also continuous at x equal to c. And if f is continuous at c, I call this as first note and this is second note. If f is continuous at x equal to c, then 1 by f is also continuous at x equal to c, provided, again the same problem will arise, that the denominator should not be equal to 0, provided f of c is not equal to 0. Okay. Then, so students, with this I will stop today's class. We will continue our discussion tomorrow.